Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 25. In this lecture, we'll discuss work, Part 2. This topic is covered in Chapter 7 of our textbook by Surway and Jowett. Recall that in a previous lecture, we discussed the notion of work. Work is a measure of the influence of forces on a system. So as forces act on objects, they bring about displacement, they cause acceleration, and in that sense, we can say that forces influence or affect objects. We'd like to have a way of quantifying that influence, and that's where work comes in. A little more precisely, we decided that for a constant force, work is defined as the magnitude of the force times magnitude of the displacement of the object times cosine of the angle between the force vector and the displacement vector. Now, this definition works only for constant forces. In this lecture, we'd like to develop a more general definition of work that also works for variable forces, for forces that change as a function of time or position. Before doing that, we also want to remind ourselves of the dot product operation, which we discussed in our last lecture. In that lecture, we defined the dot product of two vectors A and B as the product of the magnitude of vector A times the magnitude of vector B times the cosine of the angle between those two vectors. As we compare that definition to our definition of work presented here, we realize that work can also be defined as the dot product of vector F and vector delta R. So at least for a constant force, work is simply the dot product of two vectors. One is the force vector that's acting on an object, and the other is the displacement vector, which measures the motion or the amount of movement or the change in the position of an object. This new definition of work will help us generalize this definition to variable forces. So we've learned that for a constant force, work is simply the dot product of the force vector and the displacement vector. But how do we calculate work when the force is not constant, when the force is variable, when the force is changing? To have a concrete example in mind, imagine that you want to push a box or a crate, let's say, across the floor of a warehouse. You want to move this heavy box from one end of the warehouse to the other end of the warehouse. To do so, you begin by applying a large force to the box, let's say 1,000 newtons of force. But after a few meters, you get a little bit tired, so you reduce your force, let's say from 1,000 to 800 newtons. And then you get a little more tired after a few more meters, so now you reduce your force to, let's say, 500 newtons of force. And then as you get more tired, you reduce your force again. But eventually, as you're approaching your goal with renewed energy, you apply a large force to the box and you finally arrive at your destination. So how do we calculate work for this entire process where the force has basically changed 5 times? Well, we basically divide the problem into 5 stages or 5 intervals. We calculate the work for each stage and then we add those works together. So we can say that for the first stage, the force was constant at 1,000 newtons. So we will use our formula for a constant force to calculate the work. And then for the second stage, the force was constant, but a different constant, this time, let's say 800 newtons. So we'll calculate the different work there, and then we'll calculate a third work and a fourth work and a fifth work, one work for each stage or interval of this problem. And then we'll add those together to find the total work done. A little more precisely, the recipe that we're following is this. We're going to take the total distance and we're going to divide it into many intervals. Each interval or each stage will have some length delta x. We're going to calculate the work for each stage or each interval. So the work for the nth stage, like the fourth, the fifth stage, will be the force for that stage times the length of our intervals. And then we're going to calculate the total work by simply summing all of those works. So the capital sigma here refers to summation. So to calculate the work when the force is changing, we're going to sum over the forces for each stage or interval times the length of those intervals. Now, we didn't specify how large these intervals should be. If you're moving the box 100 meters, you might want to divide that distance into 100 intervals, each one 1 meter long. But it would be better if you divided it into, let's say, 10,000 intervals, each one of them only a centimeter long. In fact, it would be even better if you divided it into 100,000 intervals, each one only 1 millimeter long. In general, the smaller delta x is, the better this procedure will work. In fact, what we can do is take the limit as delta x goes to 0. In other words, we can make delta x infinitely small or infinitesimal. When that happens, what we get is an integral. In fact, you might remember from your calculus class that this is exactly how integration is defined. An integral is simply the sum of a bunch of things in the limit as those things go to 0. So as we make delta x smaller and smaller, in the limit as delta x goes to 0, this summation becomes an integral, and we get a precise value for the total work that's done in this case. So this final equation is how we're going to calculate work for variable forces. So we've just seen that to calculate the work for a variable force, we need to integrate. We need integration. Unfortunately, that result was valid for motion in one dimension only. Recall that we imagined a box being pushed along the x-axis, and therefore we had to do an integral with respect to x. We want to have a more general result. We would like to be able to push boxes in 2 or maybe even 3 dimensions and be able to calculate the work. To do that, recall that for a constant force, we decided work was the dot product of F and delta R. So it turns out the dot product allows us to easily generalize our definitions for work to 2 or 3 dimensions. Going forward, for an arbitrary force in any number of dimensions, work is defined as the integral of F dot ds. So we're using both the dot product concept and the integration concept. This is our most general definition of work. It's suitable to constant forces and variable forces. It's suitable to one-dimensional motion and two-dimensional motion and three-dimensional motion. Using this formula requires some mathematical sophistication. You have to be able to perform integrals, you have to be able to understand vectors, and you have to be able to take the dot product of the vectors. We also have some new notation here that you need to be familiar with. F with an arrow on it simply refers to the force vector. That's relatively easy to understand. However, ds is a new concept. ds is essentially an infinitesimal displacement. So it's quite similar to the delta r that we had here. However, in the limit, as this displacement vector becomes smaller and smaller, we denote it as ds. If you want a more concrete understanding of what ds is, you can think of ds as being a very small displacement in the x direction, followed by a very small displacement in the y direction. So if you want, you can even write the ds vector in components, where its x component is an infinitesimal displacement in x, and then we have an infinitesimal displacement in the y direction. So we write it as ds, however, it's really a vector with two components, one being the x displacement and the other being the y displacement. We should also point out that to evaluate this integral, we might have to know something about the path that is being followed. In other words, if you're going to move an object from point A to point B, it's important to know whether you're moving it along the shortest path or if you're taking a longer meandering path to get from point A to point B. In one-dimensional motion, that's not really an issue, but in 2 dimensions, you have options regarding how you get from point 1 to point 2. So this integral is sometimes referred to as a path integral because it depends on the path or the precise way in which you get from point A to point B. So we now have a general equation for calculating work that works for both constant and variable forces in 1 or 2 dimensions. Turns out using that equation is a mathematically sophisticated task that requires a little bit of practice. So let's do a practice problem involving a variable force in 2 dimensions. A block of mass 9 kilograms moves on a horizontal floor from coordinates 0, 0 to 3, 9 along a parabolic path. The force F is one of several forces acting on the block. Calculate the work done by this force. So again, imagine that you're pushing a box across the floor of a warehouse, but this time you're moving in 2 dimensions. So we need to consider motion in X and the Y direction. So we can set up a coordinate system like so. This is our x-axis and the y-axis. These are both horizontal axes, so they're laid down on the ground. And our goal is to move from this point, 0, 0, to, let's say, this point, which has coordinates 3 and 9. Now, we're not going to move along a perfectly straight line. Imagine that, for example, the straight line is blocked, and so we have to work our way around some obstacle. So what we're going to do is move along a parabolic path that looks like this. So you can imagine that this path is described by the following function, y equals x squared. This is simply a parabola that passes through points 0, 0 and 3, 9. Now, there are multiple forces acting on this box, but your force, the force you're applying, the force we're interested in, is described here as 3x plus 1, 0. So the force that we're interested in has a 0 y component, and it has a variable x component. A little more precisely, what that means is that the force only points in the x direction. Initially, the force points like so, and then as the x variable increases, the force becomes bigger and bigger and bigger. So these vectors pointing to the right represent this force here. Notice that there is no y component, and the x component is gradually getting bigger and bigger. You might be wondering if the force is pushing to the right, why is the object moving upwards? Why is it moving along a parabolic path? Well, that's because this force is one of several forces. So you can imagine that some of your friends or coworkers are helping you push this box, and they're pushing in different directions. We don't know what their forces are, but we don't care. At this point, we're only interested in the work done by this particular force. So now, since this is a variable force in 2 dimensions, we need to use the general definition of work that we've been talking about. And this is how we're going to proceed. So our new general definition says work is the integral of f dot ds. And now you need to remember that ds is a vector. So the ds vector can be written as follows. It can be written as dx, dy. And then, of course, the force vector in general has an x component. You can call that f sub x, and a y component, call that f sub y. And then the dot product of those 2 vectors can be carried out in 2 different ways. One way to do it is using the component definition of the dot product. So we can multiply the x's together, we can multiply the y's together, and then we could add those together. So we get fx dx plus fy dy. Now it turns out that fy is 0, so that simplifies the integral a little bit. We're told that the y component is 0, and the x component is 3x plus 1, and that's where this 3x plus 1 comes from. So now we have an integral of 3x plus 1 dx. You should be able to carry out this integral relatively easily. You do need to pay attention to the limits of integration. We are performing an x integral here, so we need the limits of integration to be x limits. In other words, the limits of integration need to correspond to the variables of integration. For us, we're going from x initial 0 to x final 3. So we're going to have to plug in those limits of integration, 0 and 3, into our integral. And when we evaluate this using our calculator, we see that the total work performed by this particular force is 16.5 joules along the entire parabolic path. This is probably the easiest way of doing this problem, but you should know that there is another way of doing this problem. Remember that there are two ways to evaluate the dot product. There is the component definition, but there's also the magnitude definition, and it might be instructive to see this alternative calculation. Here we're going to use the fact that the dot product of f and ds is simply the magnitude of f and the magnitude of ds times cosine of the angle between these two vectors. What's the magnitude of f? Well, the force vector is given to you here. Remember, to calculate the magnitude of any vector, you basically use the Pythagorean theorem on its x and y components. The y component is 0, so the magnitude of this vector just ends up being 3x plus 1. That's where this magnitude comes from. What's the magnitude of the ds vector? Well, remember that the ds vector has components dx, dy. So I'm going to square the x component, square the y component, add them together, and take the square root. So this square root here is simply the magnitude of the ds vector, which is the infinitesimal displacement vector. And then we need to know what the angle between the force vector and the displacement vector is. That's probably the trickiest part. Remember that the force vectors were pointing to the right along the x-axis. The displacement vectors are a little bit trickier because we're moving along a parabolic path, so the direction of motion is changing. Remember that the displacement vector is proportional to the velocity vector, and the velocity vector is always tangent to the path. So we can say that these displacement vectors are basically tangent to the path, to the parabola. Anyways, the angle between the displacement vector and the force vector is going to be theta, and we're interested in evaluating cosine of theta. Recall that cosine of theta is going to be basically the adjacent leg of the triangle divided by the hypotenuse. The adjacent leg is dx, and the hypotenuse is the magnitude of the displacement vector. So cosine of theta is just going to be dx divided by magnitude of the displacement vector, which we've already decided is the square root of dx squared plus dy squared. Now this expression here looks pretty horrendous and complicated to deal with, but of course it simplifies very quickly. You notice that this nasty square root cancels this nasty square root, and now we're left with a relatively simple integral here. Notice that this integral is in fact the same integral that we had up here. So if we continue to evaluate this integral, we'll get exactly the same answer, just arrived at using a slightly different way of calculating the dot product. On an exam or on the homework, you're free to use whichever technique works best for you. I think that for this particular problem, because the components were given, it's best to use the component definition of the dot product, but you can also use the magnitude definition with exactly the same result. Let's do another practice problem involving work. Consider a block with mass m near the surface of Earth. Suppose the block is initially at rest at height 0. So the block is essentially sitting on the ground. Calculate the minimum work that is necessary to raise the block to height h without imparting a final velocity to it. Now note a couple of things about this problem. First of all, we want to calculate the work done by you, not by gravity. So imagine you're trying to lift the box. As you're lifting it, gravity is pulling down on the box. So gravity is performing some work, but you're also performing some work. In fact, every force that acts on the box, on the block, is performing some work. In this problem, we're interested specifically in the work done by you, or the person lifting the block. We're also interested in the minimum work. In other words, we don't want to overexert ourselves. We just want to apply the minimum force to get the job done with the minimum amount of work. Now you might be asking, well, what is the minimum force? Well, as you lift this box from the ground to final height h, you have to remember that there are two forces acting on the block. Gravity is pulling down, so that's weight. Its magnitude is mg. And if you want to lift the box, then the force that you apply must be greater than or equal to mg. If the force you apply is less than mg, you're not going to succeed in lifting the box. So you need to overcome weight in order to get the block off the ground. So the force that you apply must be greater than or equal to mg. If you apply a force that is much greater than mg, then the block is essentially going to get launched into the air. It will reach a final height, well, it will reach a height of h, but it will continue going up into the sky after that. We're not interested in doing something like that. We want to simply lift the box to height h without giving it any kind of a final velocity. So we're not interested in launching it into the air. We're going to apply just the minimum force, meaning that the force that we'll apply will be equal to mg. So that's the lower bound or the minimum force. So given that information, we can now calculate the work as follows. Work is equal to the integral of f dot ds. F is the force vector, not the force of gravity, but the force of the person lifting the box, so your force, let's say. That's going to be 0, mg. We're trying to lift the box, so we're not going to apply a force in the x direction, and the force we're going to apply is going to be in the positive direction, and it'll be the minimum force required, which is at least the force of gravity, mg. ds, of course, is simply our infinitesimal displacement vector, dx, dy. Remember how to calculate the dot product. You multiply the x components and you multiply the y components. 0 times dx gives you 0, so the x integral disappears, and you're left with mg times dy. So now you have to do a y integral. The y coordinate has an initial value of 0 and a final value of h, so the limits of integration are 0h. You should be able to do this integral relatively easily. The integral is mgy. You plug in the limits of integration, and your final answer is mgh. So the minimum work required to lift a box to a height h is simply mgh. Remember this result. This turns out to be a very important equation. We're going to come back to this result in a couple of lectures when we start talking about energy and potential energy. For now, just remember this result as the minimum work required to lift a box. Let's do one last practice problem involving work. Consider an object with mass m. Suppose the object is initially at rest. Calculate the minimum work that is necessary to accelerate the object to speed v. Now notice something important about this problem. We are talking about the minimum work that is necessary to speed up the object. And if we're talking about the minimum work necessary, then we have to assume that there is essentially no other forces impeding or resisting the motion of the object. Specifically, we're going to assume that friction and resistive forces like air resistance and the viscous force are absent. So what we're imagining is maybe a box, an object with some mass m. We're going to imagine that it's sitting on a frictionless surface, or better yet, maybe it's just floating in outer space. And all we want to do is accelerate this object. Initially, it has a velocity of 0, and we want to apply a force to it. We want to push it, and we want to accelerate it so that after some time or some distance, its final velocity is v. Since we are imagining this thing in outer space, there's not going to be any air resistance or any friction. So this force really is the minimum force necessary. If there were friction, we would have to apply a larger force. But for now, we're just interested in the absolute minimum work and therefore the minimum force necessary. Notice that at this point, we don't really know what the force is. We have no idea what the magnitude of this force is. The only thing we can assume about it is its direction. So for now, we're going to assume that this force is in the x direction. If you want, you can imagine moving the object in the y direction or even some diagonal direction. The end result will be the same. However, it's easier for now if we just assume that we want to push the box in the x direction. So we proceed as follows. We say that work is the integral of f dot ds. Notice this is the general definition of work. You should remember this definition. On an exam, if you encounter a work problem, the very first thing you should write down is something like this. Even if you have no idea how to solve the problem, you should at least write down the definition of work, and that usually gets you some partial credit on that problem. Now, we don't exactly know what the force is, but we are assuming it's pointing in the x direction, so we're going to write the force vector as f comma 0. So its magnitude is f, its x component is f, which is unknown at this point, but its y component is 0. And then the ds vector, of course, is the infinitesimal displacement vector, which we'll write as dx comma dy. Remember that the dot product of two vectors involves multiplying the x components and multiplying the y components. When we do that, we'll get f dx. So the y integral disappears. Since we're performing an x integral, the limits of integration must correspond to x. At this point, we don't really know how far we have to push this box in order to achieve this final velocity. If it's a very light box, you might have to just push it for maybe a meter or two to achieve this final velocity. But if it's a very heavy box, then you might have to push it for a very long time to achieve that final velocity. So for now, we're just going to say we're going to push the box from initial coordinate 0 to some final coordinate x. We don't know what x is at this point. Notice there's a lot of unknowns here, but one thing we do know for sure is that F is equal to ma. So we're invoking Newton's second law of motion. Newton tells us that the net force is equal to mass times acceleration. Here we're assuming there are no other forces like friction or gravity or resistive forces. So nothing is impeding the motion of this box. The only force is this applied force. So this force here is the net force, and the net force must equal to mass times acceleration. We still don't know what the acceleration of this box is, but we do know that acceleration is the derivative of v with respect to t. So here we're using the definition of acceleration. Now, as it stands, this integral is not really possible to evaluate. However, we notice something interesting. We have dv over dt, and then we have a dx here. We can combine the dx and the dt together, so we can treat the derivative as if it's a fraction. We can move the dt over, and what we'll end up with is an integral of m dv dx dt. Notice in executing this subtle maneuver, we're basically turning an x integral into a v integral, and therefore the limits of integration have to change from x to v. Now, this doesn't really seem like a useful thing to do until you realize that dx dt is itself v. That's how velocity is defined. It's the derivative of position with respect to time. So this integral here can be written as m v dv. So I've replaced the dx dt with v. Now the mass of this object does not change as you push it around. So m is a constant. You can bring it out of the integral. And then v dv is an easy integral to do. You raise the power of v to 2, and then you divide by 2. So this integral ends up being 1/2 mv squared. Of course, you should plug in the limits of integration. We're assuming that initially the velocity was 0 and finally the velocity is v. So the end result is 1/2 mv squared. So the minimum work necessary to accelerate an object from 0 to final speed v is 1/2 mv squared. This is an incredibly important result. Remember this result. You'll see it again in a couple of lectures when we start talking about energy and in particular kinetic energy. So we'll come back to this result, but for now just remember it as the minimum work required to accelerate an object. And that's the end of this lecture. Thank you for your attention.